Welcome to Educator.com. In today's Algebra 2 lesson, we'll be discussing solving systems of equations by graphing. Recall that a system of equations for our purposes is defined as two equations in two variables. Later on, we'll be looking at systems of equations involving more than two variables, but right now we're just going to stick to this definition. For example, a system of equations could be something such as 2x minus y equals 7 when it's considered along with another equation such as x plus 3y equals negative 4. And a solution to a system of equations would be a value for x and a value for y, so a set of values that satisfies both of the equations. The first technique we're going to discuss in solving systems of equations is solving by graphing. In addition, later on, we'll be talking about how these systems can be solved algebraically. So, one way to solve is to graph each equation. The solution for the system is the point of intersection of the two graphs. And we'll do some examples in a minute, but for now, imagine that you're given an equation and you figure out some points or one of the points in the slope, and it turns out that this is the graph of the line described by the equation. And you're given another equation as part of that system. And you go ahead and you graph that one out, and it comes out to a line that looks like this. The solution for the system is a point of intersection. So this is the solution. The x and y coordinate for this point are the solution. Now, here you can see a weakness in this method, and that is if the solution doesn't land right on an integer, it's difficult to get an exact value. And that's one advantage to the algebraic methods. But if you graph carefully and the solution does land on, say, 3, 4, then you could get an exact solution. There are several types of systems of equations. We call a system independent if it has exactly one solution. For example, just as I showed you in the previous slide, sometimes you'll graph out a system, and usually in the problems you'll be doing, you'll see a single point of intersection, which is the solution, the single solution, and this set of lines describes an independent system. Other times, you'll go along and you'll graph out the system of equations. So you graph the first equation, and perhaps the graph looks like this. Then you go to graph the second equation, and it turns out that it describes the same line. So if the system of equations, both equations within that system describe the same line, then there would be an infinite number of solutions. And the reason is every single point along this line, every single set of x, y coordinates is an intersection of the two systems. The line, every single point along this line, and there's an infinite number of points along the line, is a set of solutions, a set of x, y values where the two lines intersect, since they're the same lines. Here, we call this a dependent system. So here we have one solution, here an infinite number of solutions, and this is a dependent system. The third possibility is that there is no solutions, and we call this an inconsistent system. So thinking about a situation where there would not be any solution, where there's no point of intersection, would be a set of parallel lines. So drawing this over here for clarity, so here's my xy axis, and if I graphed the first line, the first equation, linear equation, and then I went ahead and graphed the second one, and those two turned out to have the same slope, those would be parallel lines. They are never going to intersect. Therefore, we can see on the graph that there is no solution. So no solution, and that is an inconsistent system. So 3 possibilities: one solution, intersection at one point, infinite number of solutions, all the points along a line, or no solution because it's a set of parallel lines that do not intersect. So the first example gives us a system of equations with 2 variables, x plus y equals 3 and x minus y equals 1. So graphing this first line, so I'm going to start with x plus y equals 3, and I'm going to find a few x and y values, some ordered pairs, so I can do the graphing. First, I'm going to let x equal 0. Well, if x is 0, I can see easily that y is 3. So that gives me the y-intercept. Next, I'm going to let y equal 0 to find the x-intercept. So this would be 0, x would be 3. And just one more point to make it a better graph, because it's especially important when you're not just graphing one line, you're actually looking for a solution to a system of equations to have a really good graph so you can find the point of intersection accurately. So when x is 1, so x plus y equals 3, so when x is 1, y equals 2. So I'm going to graph this line. So first I have the y-intercept at 3, I have the x-intercept at 3, and another point in between those. X is 1, y is 2. And this gives me a better sense of the slope of the line than if I had just done 2 points. Okay. The second equation, graphing that, x minus y equals 1. Again, finding a few values for x and y, a few sets of values. When x is 0, so if x is 0, that would give me 0 minus y equals 1. So negative y equals 1, therefore y is negative 1. The y-intercept is negative 1. Now finding the x-intercept, let y equal 0. If y is 0, x is 1. One final point, I'm going to just let x equal 2. So that would be 2 minus y equals 1. And that's going to give me negative y equals negative 1. So y equals 1. Again, I have 3 sets of points to graph. So the y-intercept is at negative 1. The x-intercept is at 1. And one more point. When x is 2, y is 1. Okay, drawing this line, I can immediately see that I have a single point of intersection right here. This is the solution. And this occurs at 2, 1. So the solution for this is x equals 2, y equals 1. And therefore, this is an independent system. It's an independent system since it has one solution. Okay. And you can always check your work by substituting x and y values back into these equations. So I have x plus y equals 3. So that's 2 plus 1 equals 3. And that checks out. I have x minus y equals 1. So 2 minus 1 equals 1. And that checks out. So you can easily check and make sure that both of these are valid and they're valid solutions for both equations. Second example, a little bit more complicated, but using the same system. And this time, instead of just finding x, y values, I'm going to graph these out by putting both equations into slope-intercept form. So the first one, 2x minus 4y equals 12. So I'm going to subtract 2x from both sides. And then I'm going to divide both sides by negative 4. And that's going to give me y equals 1/2 x minus 3. Slope-intercept form is very helpful when you're graphing. So this is negative 2, negative 4, negative 6, negative 8, negative 10, 2, 4, 6, 8, 10. Okay, here I have a y-intercept at -3. And I know the slope. The slope is 1/2. That tells me when I increase x by 1, I'm going to increase x by 2. If I increase x by another one, I'm going to increase y by another one, increase x by 2. So you can see the slope of this line right here. That gives me enough to work with. I'm going to do the same with the second equation. 4x minus y equals 10. Putting this into slope-intercept form, y equals mx plus b, subtracting 4x from both sides, and then dividing both sides by -1 to give me y equals 4x minus 10. So here I have a y-intercept at -10 and a slope of 4. So I'm going to increase y by 4, that's 2, 4, increase x by 1. Increase y by 2, 4, increase x by 1. Increase y by 4, 2, 4, increase x by 1. Okay, so this is a much steeper line. The slope is much steeper with a slope of 4. So I'm going to go ahead and draw it like that. And the point of intersection is actually right here. And again, we have an independent system with a single solution. And it's at 2, -2. So that is my point of intersection. X is 2, y is -2. Again, you could always check your answers by substituting either or both the equations with these x and y values and ensuring that the solutions are valid. So again, I have an independent system. It has one solution, one set of valid solutions. Okay, this next example, again, solved by graphing, and my approach is going to be to put these into y-intercept form and use that to graph. First, 2x minus 3y equals 6. So -3y equals -2x plus 6. Divide both sides by -3 is going to give me -2 divided by -3 is 2/3 x. And then 6 divided by -3 is -2. So this line has a y-intercept of -2 and a slope of 2/3. So increase y by 2, increase x by 3. Okay, that's my first equation. Second equation. Again, putting it into slope-intercept form, which is an easy way of graphing. This gives me 6y equals 4x minus 12. Dividing both sides by 6 gives me 6x minus 2. And I'm going to go ahead and simplify this to 2/3 x minus 2. So you may already see that these are the same equation. These are going to describe the same line. Even if you didn't notice it right away, when you start graphing, you're going to see the y-intercept is -2, the slope is 2/3, you're going to end up with the same line. Because this is the same line, they intersect at every single point. These two equations, their graphs intersect at every single point, which is an infinite number of points along the line. They don't intersect everywhere, but everywhere on this line. Therefore, this is a dependent system, and there's an infinite number of solutions. All points along this line are solutions, and this is known as a dependent system. So initially you looked at this, you might not have recognized that these are actually describing the same line. But once you started to plot it, either by putting it in the y-intercept form or by finding points along these lines, you would have quickly realized that this is the same line. In this last example, again, a set of equations, a system of equations that we need to solve by graphing. Again, using the method of slope-intercept form for graphing, 4x minus 2y equals 8, subtracting 4x from both sides, and then dividing both sides by negative 2 to give me y equals 2x minus 4. Okay, the y-intercept is negative 4. The slope is 2. Increase y by 2, increase x by 1. Increase y by 2, increase x by 1, and so on. I have 3 points. That's plenty to graph this line. So that is my first line. Second line, again, slope-intercept form. Add 6x to both sides, gives you 3y equals 6x plus 12. Now, dividing both sides by 3 to get y equals 2x plus 4. So here I have a y-intercept of 4 and a slope of 2. So increase x by 2, increase y by 1. So I'm going to get a line looking like this. And what you'll see, what you may quickly realize, is that these are parallel lines. One thing you could have noted is that the slope, m, equals 2 for this line, and it equals 2 for this line. Since these are parallel lines, they are never going to intersect. And this is an inconsistent system, and there is no solution. And what we say here is that you could say the solution is just empty set. There's no solution. This is described as an inconsistent system. Okay, that concludes this lesson of Educator.com describing graphing to solve systems of equations. And I'll see you next time.